Hi, today we are going to start chapter 6, and chapter 6 is all on the periodic table. We're going to look at a lot of what we saw in chapter 5, electron configurations, how that gets applied to the properties of particular elements, and then we will take that into how compounds are formed. So first, let's start by looking a little bit at what is, or how the periodic table came to be. So for many years, chemists and before that alchemists were starting to figure out what exactly an element is, and they would take substances and try and break them down, and in that way they found a lot of elements, and they found some substances that they thought were elements that wind up not being. But around the mid to late 1800s, scientists started to become more sophisticated and really start to figure out what makes an element an element. And then they wanted to try and organize these elements, see if they could find some sort of pattern to it. There were a few different chemists or scientists who tried to do some work with this. There was this idea that maybe elements came in triads, so that there were 3 elements that had similar properties. And, copper, silver, and gold have very similar properties. Sodium, potassium, lithium have very similar properties. Newlands was a chemist who came up with this idea of the law of octaves, and he thought that elements would basically repeat like every 8. And in some ways they were not wrong, but they just didn't know the full story. The scientist who's generally credited with discovering or inventing the first periodic table was a guy by the name of Dmitry Mendeleev. He was Russian, and he's got a very interesting story. There's some really cool videos on the Schoology page if you want to learn more about the discovery of the periodic table and Mendeleev's role. But basically, he had figured out, or a group of scientists had figured out, how to accurately measure the average atomic mass of an element. And so when he started to arrange his periodic table, the first thing they did is he put elements in order of increasing average atomic mass. And then after he did that, he started to notice and started to look at their properties, and did notice that there were some properties that did repeat. And other scientists had done similar activities, such as Mendeleev. But what made him stand apart was that he left empty spaces. He recognized that perhaps we hadn't discovered all the elements that there are. And he left spaces and then predicted what would be the properties of them based upon sort of the whole that they occupied. He predicted their mass, whether they would be metals or non-metals, good conductors or bad conductors. And a few years later, those elements were found. And once those elements were found, it was really then regarded that his periodic table was probably the best way of organizing the elements. But remember that he was organizing them by increasing average atomic mass. And when we look at a periodic table today, we'll notice that there are actually a few places where the average atomic mass doesn't always increase. It's a very small percentage of the time, but that isn't always true. What is always true is that atomic number always increases. Why didn't Dmitry Mendeleev organize the periodic table by increasing atomic number? They just didn't have a way to figure out atomic number yet. That was in the mid to late 1800s. It wasn't until around 1913 that a British man by the name of Henry Moseley actually did some research and was able to figure out how many protons there were in every element. What this also eliminated was the idea that maybe there could be elements in between the elements that were discovered. Now we knew element 1, element 2, element 3. So Henry Moseley rearranged the periodic table in order of increasing atomic number. And now what we have is this thing called the periodic law, which is basically, if someone says, how is the periodic table organized? You would say, well, it's the periodic law, that there's a periodic repetition of chemical and physical properties of the elements when they are arranged by increasing atomic number. And so now let's start talking about just some vocabulary surrounding the periodic table so that when we start talking about it, we will be using the right terms. So we will often talk about the groups of the periodic table. And you can see groups are the vertical columns. The vertical columns in the periodic table, and they generally have similar properties to one another because they have the same number of valence electrons. You've certainly heard about valence electrons in other science classes. We're going to talk about them more in here as well. And periods are the rows of the periodic table, the horizontal rows. And those will not have similar properties. What they do have in common is that they have the same number of energy levels. When you've studied in the previous chapter, we looked at Bohr model and that there were those concentric rings, those energy levels. So anything that's any two elements in the same period would have the same number of energy levels. Okay, those are numbered. The periods are numbered 1 through 7, and the groups are numbered 1 through 18 all the way across. We don't have groups for those lanthanide and actinide series. So now let's get into that more information about valence electrons. Valence electrons are those outermost electrons in elements, and they are primarily responsible for the properties of those elements. And you'll remember from electron configuration, when we say the outermost electrons, we mean the highest energy level that's occupied. So if I think of magnesium, right? If we do magnesium's electron configuration, 1s2, 2s2, 2p6, 3s2. The highest occupied energy level is the third energy level, and there are 2 electrons in it. Magnesium, and everything in magnesium's column, has 2 valence electrons. Everything in hydrogen's column has 1 valence electron, right? If we were doing their electron configurations, for example, sodium would end in 3s1. Potassium would end in 4s1. They would all have 1 valence electron. Now, if we keep going all the way across, right, boron would end in 2s2, 2p1. So those are the same energy levels. So I add up the total number of valence electrons. 2 plus 1 is 3. And everything in boron's column has 3. Carbon's column has 4. Nitrogen's 5. Oxygen is 6. Fluorine is 7. And then helium, it only has 2 electrons, so it has 2 valence electrons. But then neon and everything below neon has 8 valence electrons. And valence electrons are going to become very important when we start talking about bonding and properties. Let me just make this a little bit smaller up here, because students often ask, well, what's going on with all of these guys? Remember, if we were going to look at, chromium or vanadium or titanium's electron configuration, they would all end in 4s2, 3d, and then it would depend. It would be 3d1, 3d2, 3d3. So that means that they all have the same number of valence electrons, and that's 2. Same thing with the lanthanide and actinide series. But I have to say, the number of valence electrons is not as important with their bonding as with the elements in the S block and the P block. So just looking a little bit more about valence electrons here. These are the valence electrons in the second period of the periodic table. So we can start with, in the upper right-hand corner, if we take a look at this element, 3 protons. Well, 3 protons means that it is lithium. And if we are talking about lithium, right, you can see it's 2 core electrons here in yellow, and then it's 1 valence electron, that electron in the outermost energy level. Next, with 4 protons total, we're at beryllium with 2 valence electrons. You can see the 2 blue circles there. Now we have 3 valence electrons, and that would be boron. Carbon has 4 valence electrons. Nitrogen has its 5 valence electrons. Oxygen has 6. Fluorine, my favorite element, has 7. And then at the end, you have neon, which is filled. Every element would be considered filled with 8 electrons, except for a very few. So those are in that first full row across, the second period. So if you look at the first 3 here, these atoms with an incomplete electron shell or an electron level, if they only have a few valence electrons, and when I say a few, maybe less than or equal to 3, then what they tend to do is they tend to lose their valence electrons in order to become more stable. The most stable electron configuration is when its outermost energy level is full with 8 electrons. So these guys tend to lose electrons to become more stable to obtain noble gas configuration. In the middle here, it says atoms want to obtain an electron configuration like a noble gas. And when we say want, remember, elements don't want anything. They're not humans, but they are most stable. So I'm just going to rewrite that to remind us that that's what we're really talking about, right? If the atom cannot, an electron configuration with half filled is best. And we saw that a little bit when we were looking at the electron configurations and orbital diagrams with the arrows back in chapter 5. Atoms with incomplete electron shells with more than, let's say 5 or more valence electrons tend to gain electrons to be more stable. So nitrogen, oxygen, fluorine, those guys gain electrons to be stable. What about carbon in the middle? Carbon will do, could sort of do either, but actually what it does is mostly it just shares electrons. It only covalently bonds. Right? So valence electrons are the electrons in the outermost energy level. Just as a review, they are held more loosely by the atom. Those ones that are further from the nucleus, think of Coulomb's law, they're less attracted to the nucleus. They're held more loosely in the atom. And atoms in the same group, column up and down, generally have the same number of valence electrons. And again, electron configurations with filled energy levels are the most stable electron configurations. This is why noble gases don't need to react or bond. Right? Noble gases don't react or bond with any other substances in nature. We can make them do it in a lab, but that's because they already have that filled outermost energy level. They're already really stable.